In the year 1859, communication technology was vastly different from what we have today. There was no such thing as cell phones, text messaging, or social media. If you wanted to send a message fast and over long distances, you would send it via telegraph. It was during this time that one of the most intense and well-documented geomagnetic storms in recorded history occurred, which became known as the Carrington Event. The storm was named after the English astronomer Richard Carrington. He and another English astronomer, Richard Hodgson, observed an intense solar flare on the Sun on the 1st of September 1859. The Sun's ejected energy and particles from this event reached Earth just a little over 17 hours later. The Carrington Event caused widespread disruption to telegraph systems around the world. Telegraph operators reported receiving electrical shocks, and some equipment even caught fire. Operators also reported that they were still able to send messages to each other even if they unhooked their batteries. The aurora borealis, normally only visible in high latitudes, was seen as far south as Cuba and Hawaii. The auroras were so bright that people in the northern United States could read newspapers by their light. The severity of the event marked a turning point in the interest in the study of space weather and its impacts on our lives. If a Carrington-level event were to occur today, the effects would be catastrophic. Our modern world is dependent on technology that is vulnerable to the effects of solar storms. Power grids could fail, satellite communication could be disrupted, and electronic devices could be permanently damaged. Solar flares and coronal mass ejections, or CMEs, are two phenomena that originate from the Sun and are related to the activity of its magnetic field. A solar flare is a sudden, intense burst of energy that occurs on the Sun's surface. It is caused by the release of magnetic energy stored in the Sun's corona, which is the outermost layer of the Sun's atmosphere. Solar flares can release the energy equivalent to billions of atomic bombs and are among the most powerful explosions in the solar system. CMEs, on the other hand, are massive eruptions of plasma and magnetic fields from the Sun's corona. Like solar flares, they are triggered by the Sun's magnetic activity, but they involve a much larger amount of material, sometimes up to 10 times of a solar flare. CMEs can travel at speeds of up to several million miles per hour and can take days or even weeks to reach Earth. Both solar flares and CMEs are closely related to the Sun's 11-year activity cycle, during which the Sun's magnetic field undergoes a complete reversal. At the peak of the activity cycle, which is known as the solar maximum, the Sun is more prone to produce solar flares and CMEs. Conversely, during the solar minimum, the Sun's magnetic field is more stable, and these phenomena are less frequent. The Earth's magnetic field is a critical component in protecting life on our planet. It acts like a shield, deflecting the majority of harmful charged particles and radiation from the Sun. The magnetic field is generated deep within the Earth's core, where hot molten iron generates electric currents that produce a magnetic field. This field extends far beyond the surface of the Earth and forms a protective bubble called the magnetosphere. Some of the charged particles that do manage to penetrate the magnetosphere are funneled toward the poles, where they collide with gases in the Earth's atmosphere, producing colorful auroras. Without the Earth's magnetic field, the solar wind and charged particles from the Sun would strip away the Earth's atmosphere and make life on planet Earth impossible. This has happened on other planets in our solar system, such as Mars. Scientists believe that the absence of a protective magnetic field is one of the main reasons why Mars lost its atmosphere and became the barren, desert-like planet we know today. The Carrington Event was a wake-up call for scientists, and it sparked a new era of solar research. Today, we have a much better understanding of the Sun and its behavior, but there is still much more to learn. Comment below on what you'd do if the same event were to happen again.